Good morning, I'm Matt Fitzpatrick. I'm the data management coordinator for Waste Site Cleanup, and I'm going to present to you the results of a recent project which was done with WPI.
Let me sit on that.
Okay.
Yeah.
I'm used to this. So, the project worked with the WPI Data Science Department, and what we've done is we've done a project with them so that the students get experience in working with the client, real-time data, real data, and the department is exposed to new technologies. Okay? So the goal of this project was to create a predictive model using machine learning to identify if an IRA submittal had an assertive statement for a risk condition. Indoor air is impacted, private wells impacted. And we had some really great students. Juan Lu, Rushikesh is here with me, and Yipan and Yun Ying. And the mentors of Mark Bodley and myself with advisors Fatima Emdad and Chunkit Nagan. All right. So it actually is an evolution of what we've done in MassDEP for the past 35 years. Initially, you started with the administrative record of little numbers and little letters and little boxes. We moved on to business intelligence, performance metrics, subsets of the regulated community, who's naughty, who's nice. And now we've moved, in this project, to data analytics, which is to draw insights into the regulated community and identify correlations and performance. So natural language processing is all around us. You see lots of examples with machine translation, Google Translator, information retrieval. Paul Locke has a cool YouTube on how to find different things in DEP submittals if you're looking for a certain type of technique or technology. Sentiment analysis, Yelp, movie reviews, that kind of stuff. A question and answering. What's the temperature out? What's the traffic? When's my flight? And then information extraction is what this project is. All right, so this is the methodology we had. The first thing to do is understand the data. You know, what information do we have? How can we use it to develop and train a predictive model and to achieve a project goal? And that data cleaning is, can we read the documents? What part of the documents really matter? Is there any text that interferes with the information we're trying to process? And then natural language processing is basically we read words and computers read numbers. And then artificial neural networks are computing systems which vaguely resemble the thought process of a brain. And it's pretty impressive because the average brain has 100 billion neurons, and each neuron has 10,000 connections. So it's pretty cool. All right, so understanding the data. Everybody knows what an IRA submittal looks like and a text screen form looks like. So submittal comes in, a DEP employee reads it, and then they check off little boxes for a series of questions. Yes, no, maybe. These questions are assembled in a spreadsheet, calibrated, so we can see for an RTN, type of submittal, town, the data was received, data was screened, and any one of 5 different flag conditions. Exceeding GW2 without indoor air sampling. Indoor air is impacted. Greater than a half inch in Apple. Private well impacted, public water supply impacted. So in order to find this information, such as site contaminants impacting indoor air, we want to find that in a report. All right? So you have flag words. You're looking for impact, effect, contaminate, exceeds, media, soil, groundwater, indoor air, private well, public well, monitoring well, modifier, greater than, less than, exceeds, and of course chemicals. And this data cleaning part is really important. It's focusing, the computer is focusing on what it actually needs to understand. So first thing the students did is they created a web crawler, downloaded a whole bunch of IRA reports from the public portal that everybody else uses. And then a funny thing is, many of the reports are locked. So the PDFs, you can't cut and paste, you can't print. I've had reports you can't even open. So what we use is publicly available tools to unlock the reports and pull the information out and just have text. So now we have text. We take the whole report and dump every word, every number, everything out of it into a text file. So what we're looking for is the keywords, flag words. So only those sentences, if we're looking for a certain statement, we're only looking for those sentences that have a keyword flag word. There's images in the reports. These are confounding factors, images and tables, because they have keywords in it. But they are not assertive sentences. They don't contain assertive sentences. So that's a confounding issue. I said we read words, computers read numbers. Lots of numbers in these reports that are non-essential. Telephone numbers, addresses, RTNs, all the numbers in tables. When you're trying to convert words to numbers and it's already a number and it's not essential, it's confounding. And then annotating the extracted sentences. So for the previous slide where I showed the submittal, the text screen, and the scoring, we know we have the answer set of what text screens had flag conditions in. But we don't know which sentences in that report. So we have to go back and annotate which sentences actually had. Just because they had a keyword doesn't mean it actually had an assertive statement for flag condition. All right. Let's see. All right. Now we're going on to what I just said about numbers. All right. So the computer is going to convert a word into a number in some manner which gives it meaning. All right. So for these 6 words, we have 3 dimensions picked at random. All right. So royalty, we have king and queen. They rate high in royalty. Man and woman, low in royalty. Femininity, queen is high, king is the inverse. Similarly for man and woman. Okay? Intelligence. Everybody's equal. Just because you're in charge of everything doesn't mean you're the smartest guy in the room. But in the way that what we've done here in this report is we use 2 different ways to convert words to vectors. Term frequency, inverse document frequency. Or a function based on how many times a word occurs in a document and how many documents, of all the documents you're reading, that word occurs in. And what this does is get rid of little words. And it gives import or weight to those words that are important. Skip Graham neighbor word prediction is another way of converting to a vector which associates the order of words in the document. So indoor air together, private well. So impacted private well. So these phrases, it gives weight to these phrases, okay? I know I'm moving really fast, but I don't have much time. So now we get to the cool stuff. Neurons and a neural net. There's 100 billion of these in our brains, most of us. And each one has 10,000 connections. All right? So when we hear something or we eat something, we have an input layer. So we all have all these neurons and nerves receiving input. And they process the input, each neuron, and then they send out signals to other neurons through its 10,000 connections. So each time it's processing and sending weighted information to the next one. to the next one until you get output. Oh, I just ate a Danish. I like a Danish. Like this with a second. Right? Okay. So common themes I'd like to emphasize these are nodes. These nodes are neurons, and this is what we simulate in the computer model, these nodes. And as they take the information in, they give weighted answers to the next node as output. All right? And the common theme you should pick up at this point is that dimensionality. So the words, we're imparting dimensions to them, many dimensions, many dimensions. Neurons have 10,000 connections, or the ability to send signals 10,000 ways. All right? So we have dimensionality, vectors, and layers. And that's how the information is directed from layer to layer. All right? So, all right. So, I'll quickly go over this. There's two different neural network models that were employed. One is long short-term memory, and the other is convolutional neural network. Now, long short-term memory, basically, you have input. You either like it or don't like it. And when you like things, you remember what you like because you want to do it again. So, I ate a hot dog. It's a Nathan's hot dog. I like a Nathan's hot dog. I eat a hot dog. It's a ballpark hot dog. I don't like ballpark hot dog. As I do things I like, I give weight to, and I remember those. And the weight stores it. Convolutional neural network is slightly different. If you think of looking at a picture, if you look at just a small segment of a picture, you don't get the whole picture. And as you move that small frame around, you see differences in the picture. So if you look at a cat, and you look at the body of the cat, you see fur. It's like, oh, that's fur. Then you move up, you see, oh, there's a chin, or there's whiskers. Oh, it's an animal. What kind of animal? And as you move around, you realize it's not a dog, it's not a hedgehog, it's a cat. So each frame that you look at has certain important features that you note and compile and aggregate or pool as you go from layer to layer. All right? So that's in less than 10 minutes the approach we use. Now we have results, which Rushikesh will go over.
Am I audible? So, as Matthew told everyone about the data cleaning process. So, the size of the reports is extremely important to us because the workstation or our computer or the memory in our computer does not take so much information in terms of sentences, and those sentences, when we multiply it with the number of reports that we have, it causes a huge deal of computation time in actually making the model learn about information about the exposure condition. So the method that we applied is that we use the preliminary action forms, and on those forms we have certain keywords, which is monitoring well, a groundwater, private water supply, and etc. Using that, we extracted all the sentences that consisted of these keywords. So based on that, if we can see from the output, we have a sentence here which is the fourth one, which clearly asserts that there is a risk condition involved here. So doing this, the entire report may be of a large size, but after doing this keyword extraction, the report goes down to just merely few sentences. Now, these sentences are only with respect to one single media, which is the monitoring well. We have multiple amount of these number of sentences with each media, and also with each flag word which is impacted, affected, exceeds, etc. So we want to have a clear assertion that there has been an exposure condition which has been found in a particular leak. So this is what it shows, and this is the input which gets converted into a number, and those numbers go into the model. So yeah. So before getting into long short-term memory, I would like to explain about how it gets converted into numbers. So as we saw from here, this is a particular set of sentences. Now from this, the model, when it converts words into numbers, which is understood by the computer, what happens is that it learns how a particular sentence has been structured. The structure of the sentence is very important here because the assertions are in a particular format or follows a particular format. So therefore, the assertions have been the assertions get converted into a vector, and for each word there is a particular probability involved that a particular word is followed by or preceded by a particular word. For example, if we have LNAPL, then we know that the probability of less than or more than half inch is going to be extremely high. The probability of this particular word being close to LNAPL is going to be very high. The probability of this monitoring well being close to LNAPL is going to be very high. And all the rest of the words, they're going to be a little lower. So that is how the system understands the formulation of each of the sentences. Going on to long short-term memory, which is the first type of model that we use. How this works is that when you are having food since your childhood, you actually know what type of food that you like. But that has been just instructed into your mind, or you have been eating it the same thing again and again and again. But you might not remember what you have eaten 1 week back. So that is how the system works. It knows what type of memory it should keep and what type of memory it should remove. It learns continuously from all the reports that is coming in from the input, and it trains itself in understanding what are the patterns that define a particular exposure condition. And then it gives the output with learning all those things. And when we give the input in the form of a new report which comes in, it reads the entire report and understands if there is any pattern involved in the memory of this particular model. The second one, as Matthew explained, how convolutional neural network work is that it forms the smallest of frames. Each frame represents a particular feature in the entire image. Now, so this is exactly how our eye works. Our retina is actually currently considering all of these pixels, each of these pixels, and then we formulate a particular image. And this image is what we see here. Exactly how the system works in the convolutional neural network is that it takes a lot of images continuously. It has a lot of data about how a particular image of the dog works. A dog is. It has the data of each of the frames of a particular dog, and when a new image of a dog comes in, it learns from all of these pages. It then formulates them into one single page. It pulls them together and then defines if this particular image is a dog, cat, or lion. Now, for these steps here, these are unknown to us because this is exactly how our brain works. So, for example, if I tell if yesterday when I knew that today I have a presentation for this project, so I didn't have to tell anything to my brain. My brain already just gave me an output that I will be excited as well as I'll be nervous for the presentation. I don't know how it works, but it just works like that. So this black box is exactly how the neurons work in our brain. We don't know how it works, but it gives the desired output that we should have in order to give the presentation clarity. So just as the image works, it is the exact same method for the text file that we have in the form of reports. This is an entire, these are all the words in our report. This is a sample image. These are not the words from the actual report, but this is exactly how it works. So each of these words have a particular vector which is provided to it. After these vectors, these are all pulled together into one single system, which is not provided to us, or it is not known to us what the system actually thinks. Looking at all of this, it forms a particular probability or numbers for each of these words being very close to each other. Based on these patterns, then it defines the pooling layer where it clubs everything together or merges everything together, and it gives the output of whether it is a positive risk condition or not a risk condition. Now the output. So I'll just explain the graph very quickly. So what the graph shows that what is the accuracy or the percentage of the reports which are classified as risk or not a risk or exposure or not exposure based on the number of times we trade it. So what is default? So imagine that we are currently in the state we are. So everyone tells us that we always learn from our mistakes. So how do we learn from our mistakes is that we just go back in time, we think about it, the mistakes that we have done, we just try to improve those mistakes. And that is exactly what epoch does. So at the first 10 epochs, at each step, the model is performing the entire step, coming to the output and then going back, learning where it did the mistakes, then again going forward and coming back. It does this 50 times, and over the period of time, it learns from its mistake and increases the accuracy of the risk condition. So this is how it increases the risk conditions, the probability or the prediction accuracy, and we have an accuracy of close to 70% for the risk conditions and a 90% accuracy for the negative condition. This is because the number of not an exposure conditions or reports in our data set was extremely high. So so what happened for our model is that it does not have the amount of data it requires in order to learn a particular risk condition. However, on the other hand, the convolutional neural network is extremely powerful in learning patterns, even if the amount of data is very low. How it is being done is that we can add a punishment every time it does a wrong prediction on a particular risk condition. So therefore, the prediction accuracy for the positive conditions where it is an actual risk condition is very, very high, and the accuracy for the negative condition where it is not is low. So what accuracy means is that what is the percentage of exposures that have been predicted as an exposure, and what are the percentage of exposures which are not a risk but it has been predicted as a risk. So we wanted this number to be extremely high, and therefore we added a punishment on the positive conditions. And we got 96% accuracy on the flat conditions and 85% on the negative conditions. So for summary, I would like to call Matthew again.
Thank you, Rushikesh. All right, so this exercise was cool. But more than that, it shows that we can utilize this technology to answer questions from the data set, or from all of our data, both structured and unstructured reports. Now, we just use unstructured IRA reports, and we use structured text screen forms. Right? Now, we can do the same exercise with another question using census data, assessor data, GIS data layers. So you can say, is there a correlation between changes in property value for square foot of population for someone that uses a certain phase 3 approach that gets stuck in a temporary solution? I mean, as an example, Worcester got a minor league baseball team, and all of a sudden these brownfield sites in the immediate area are all cleaned up. They're all popping. So we can do a lot. Now, the department has been introduced to leveraging document content. There's all sorts of questions you can ask. And I guess we're not going to have the right questions or right answers now, but we should be prepared to use this technology in the future. There's 1.3 billion devices listening to us every day. Google Assistant, Siri, Alexa, Cortana, Bixby. They're doing it, and that's every day, listening to people. And that's not counting businesses that are using the same techniques that we don't know about for for mortgages, job applicants. A lot of them to sell you beer and bubble gum. So things are changing, and we just need to be poised to take advantage of it. All right? So I know it's a lot, and I know it was really fast. Does anybody have any questions?
What were the flag conditions that were the focus of the inquiry? I mean, it's the descriptions were very abstract, and so I wasn't clear on.
So if you go to a technical screen form and you look at the first page, there'll be little flags next to 5 questions. So. So you can see little flags. So there's 5. If you go to a text screen form, you see 5 little flags.
I'm not following. What were you looking for? What did you find?
What do the flags represent, man?
So when a report comes in and a staff person text screens it, the second page on the text screen form always has the same questions. And of those questions, there are 5 with flag conditions. And if somebody answers yes or maybe to these conditions, then the department's going to do something. They'll call the LSP. They'll conduct a level 2 audit.
It's an IRA form.
It's an IRA form, but this
I'm
page,
familiar with the
Oh,
this
okay.
page occurs in every text screen form.
So that's the flag, like that there's a GW2 exceedance
Yeah, there's,
at a residence or a school.
right.
And they're using the form as
To flag.
like what is true, and then they're trying to confirm that
Right,
from the report
right.
instead of having a person review.
Right, so all this exercise is doing is, as things come in, it's going to look at them and it's going to create a flag. And we have a standard report of everything that comes in the report. And it's just going to put a little flag on it. And what it also does is supervisors can see, did someone text screen that? So in other words, we can see it, mark it, and manage productivity. So for us, but that's the implementation of this, for this question. But there's a lot of questions you can ask. And a lot of data you can use. This is a very limited one, which was picked specifically to learn how it's done. Because we got tons of data. Yes?
Couldn't you just have those boxes on a transmittal form and say, the LP's gonna check that box if that's good, and then I get those.
Yeah. But at the same time, the department has to check those boxes too. We gotta look. That's our job.
Well, I think part of the point of this project was to look at, and it's kind of proof of concept, see what we can do. And the questions that we want you to think about is, okay, if we start looking at reports coming in using artificial intelligence, kind of what questions can we ask and what can we do? So here, we already have a set of documents that were screened by DEP staff. So we have the incoming documents which the project looked at and to see, and correct me if I'm wrong, kind of the accuracy numbers that we saw before were reflecting of, did the results of the artificial intelligence evaluation kind of agree with, concur with DEP's view of those documents having gone through the text screen? So at very simplest, going into the future, if we have this set up, the documents come in, are immediately read, and rather than having DEP staff go through and fill out the checklist, it automatically gets flagged. So one question is, true, we could have rearrange the transmittal forms and identifying, have people essentially fill out tech screens, and there. As we heard on the lab audit, having people check off that the analyses were CAM compliant doesn't necessarily work, and they would still have to be a check one way or another, even if we kind of changed the transmittal forms to reflect these questions. We still want to have that check. And then the other thing is you could use it for new things that come up that aren't on the transmittal forms or the checklist. One of the questions we have now are, might be, are there sites out there where there are conditions that, the TCE sites, the indoor air, something like this would have been very useful to screen all of our old documents to identify conditions that TCE and indoor air might be a problem, given the changes in how we look at vapor intrusion and TCE toxicity. So it's both a tool for prospective use and for evaluating the reports that we've already come in for new questions that might come up. It really is, we have a huge resource here. And it's fascinating kind of, if we have tools like this, how you can then start asking questions, not only from a regulatory perspective, but from a research perspective. There's a lot of information that has been gathered that we could use, researchers could use, geologists could use, for a variety of different purposes. So we see it can work. And our as well.
Do you think that DEP will get to the point where they would turn all of this over to artificial intelligence and not have to have staff go back and make sure that some of the stuff that should have been an imminent hazard, because it's not 100% accurate?
No, I think, we're years away from anything of training all over to artificial intelligence. But I think this is one of the ways that we're using technology, or can use technology, to balance the fact that staff only have so much time, and it takes time to read through a 200-page report.
But the question is, I appreciate that, it's a great project, but at some point, in order not to have the staff do this, you have to trust this entirely. The question is,
I don't think we're.
I think that's an improper use. I think the proper use, previously you have the administrative record. That's how we started. Little numbers, little letters, and little boxes. We went to business intelligence, which is performance metrics, subsets of the regulated community. Who's doing what? Have they done? Have they submitted a report? Give me all the people that haven't submitted a report for an IRA in 6 months. That's easy. Now, we have insight into how people are moving through the MCP process. You can ask all sorts of questions about how they move through the process based on what they've done and what other people have done. So in other words, you can see other people's success for the similar conditions and see, do you match that? Or do you not match that? And why? Do you need more assistance?
So you could see...
It really becomes a question of how smart does the artificial intelligence get?
Right.
Does it get smarter than we are? Which is a pretty big question from a societal perspective.
or even as smart.
Yeah, it's accelerating rapidly.
No kidding.
But it would be interesting to use it for things like Matthew, what you're saying, to compare the progress of a particular site that has some sort of typical conditions. And if this site is lagging behind in the assessment cleanup process and there doesn't seem to be anything different about it, artificial intelligence can compare the progress of one site versus what it should be, what other sites with similar characteristics are. So it could be a way of identifying sites that need additional assistance, that use enforcement, that have financial problems. So it's it could be a grand way of screening things, at least in my view right now, this is kind of the point, to identify things so that the humans focus on a smaller number of more important questions.
I think you could use this for PFAS, to start screening where are the sites that I should be concerned about. Start screening AFFF, overturned trucks, all these. I mean, some things you've done already as a human, But there's lots and lots of little spills that have happened and little problems that we didn't capture.
Yeah, we're just beginning to make use of our ability to read those PDF documents.
Right.
Yeah.
Yeah.
So we thought it would be really cool to kind of hear, where we can go and where, the world at large, but DEP is trying to catch up
Yep.
to it.
We all are.
We all are.
Yeah. Thank you. That was great.
Thank you.
And it's really cool having the students from WPI doing this. I mean, this is all on them and Matthew for his oversight.